Session is Matthew Chantry from the European Centre for Medium Range Weather Forecasts, and will tell us about machine learning and weather forecasting and marriage of pragmatism.
Yes, thank you very much.
Thank you.
Hello everyone, I hope everyone had a nice lunch. We're going to start, wait, is this clicker working? Yes, so we're going to start to see who's awake and who's not. This is a quiz question. Are these images of rain and snow of Oxford or Cambridge? So have hands raised for Oxford, please. Okay, and hands raised for Cambridge. Okay, I'm afraid I presented you with a false dichotomy because they are AI-generated weather with a prompt of rain in Cambridge or snow in Cambridge. So you can have half marks if you said Cambridge, although I think it would have given me very similar images if I showed it, if I said rain or snow in Oxford. So this might give us great hope, right, that machine learning is going to be a wonderful tool for weather forecasting. But if we maybe play with the same fun tools online a little bit more and give it some prompts that are a bit more specific to things we're interested in, and so we ask a prompt of correcting a weather model or prompt of atmospheric heating, which we're coming up to, then, I mean, this, we can maybe see what it's gone after, and this one, yes, well, probably the less said about it, the better. So the question is really, which regime are we going to be in for machine learning in weather forecasting? Are we going to be in here where we know we're asking the right questions that we should expect it to get the answers to, or are we going to be in here where we might accidentally get something that isn't much use whatsoever? So weather forecasts without machine learning have been on a very steady but always up view over the last few decades. So this is just one measure of forecast skill from our ECMWF model. These are different lead times, so 3, 5, 7, and 10 days, showing perhaps you could argue a slowing of progress, but still an inexorable progress towards hopefully better and better models. And so the question that we're facing at the moment is, can machine learning help with this? Can it keep us on the upward track? Can it add to this? And so why have we not got to 100% forecast skill for all days already? Well, there's lots of elements to this question, but a few of the challenges of weather forecasting is that we have a limited time, because our forecasts need to be delivered in a timely manner. We have maybe incomplete and imperfect observations, and we have, as Tim sort of alluded to, computational power, which limits our grid resolution and requires closure schemes that we looked at, that we heard about earlier. So with all these challenges, we still have to produce an accurate forecast. So are these challenges of machine learning, of weather forecasting, opportunities for machine learning? So here's a few sort of ways we might think about deploying machine learning to help. So perhaps this might be acceleration through emulation, which can help with our time and computer power. It could be new observation operators to allow us to incorporate observations we've not yet considered, or to flag even observations that we think are spurious. Or it could be about synthetic resolution, so adding extra resolution that we can't afford to run natively on the grid, or improvement on our closure schemes. And I'm going to just touch on two of these. This isn't an exhaustive list, either of the challenges or of the opportunities, but it's just to show you that in my perspective, we're not limited to sort of one sort of golden bullet as an answer of where machine learning should be used for weather forecasting, but there's a whole host of possible ideas, and the challenge in this current era is to establish which ones are worthwhile pursuing all the way and which ones might die along the way. Were good ideas that didn't turn out to be good realities. So, parameterized physics, Tim told us a little bit before, and we've heard even in earlier talks about this. So these are aspects of our physical system that we can't afford to represent on our grid. And so we have to come up with closure schemes that try and get the impact on the grid that we do have from the things that we don't know. So this is an underdetermined problem that we typically solve actually in each column independently. So we have very nice scaling. We run them all at the same time, although it does limit the approximation of the system. But this means it's possibly a very nice application for machine learning, which loves to do the same task over and over again in parallel at improved performance. So, how might machine learning be used for parameterized physics? Well, again, we heard about this a little bit, so I'm just going to touch very quickly. I see there as being sort of three approaches that you could maybe blur the lines between. The first is to emulate an existing component, and you want to do this to reduce the computational cost and also to allow you to use maybe hardware that you don't know how to do already. So maybe converting part of your model into something that runs on a GPU or even an FPGA, so these very advanced pieces of hardware is quite a lot of work. So maybe machine learning can be a shortcut to do that. And there are examples of this, in fact, going back even to the 1990s, where there was sort of a brief dawn of this that then died away for reasons of basically machine learning was still in its infancy there, or neural networks were. There's then trying to emulate increased complexity model components. So someone has come up with some better approximation of the equations, but it's too expensive to run. And so you're going to do a similar thing, but here you've got the chance to improve your model, right? You don't just make it run 5 minutes faster, but you get some better performance out at the end. And then the third one is to either use high-resolution simulations or observations to generate a brand new parameterization scheme, learn some representation of physics that we didn't know before. So I'm going to be talking about some work we've been doing on radiative transfer, and this is really in actually both of these columns, so both emulating an existing model component, and there's degrees to which we know better versions of radiative transfer equations, so we could move in the future into this middle column. And so here we have lots of physical processes going on. We have the interaction with gases and aerosols and clouds, all of which to give us what is the impact from surface cooling or incoming solar radiation heating on our changes to temperature. So it's a very, very important scheme in either a weather or climate forecasting model, and there's a lot of nonlinearity in this. So how do we want to do this? I think one of the key aspects we're sort of realizing at the moment in this field, because hopefully what I showed you here is this is a very active area. All of these elements, it's a very active area. Lots of people are trying stuff, lots of people are learning things, and one of the things we've been learning recently is how important it is to keep a human in the loop and to bake in as much of our prior knowledge about the system as possible. And so if you're looking at a neural network and pick up sort of my first neural network out of the system, you get a sort of fully connected layer, a fully connected multi-layer perceptron, and it looks something like this. You have all sorts of very complicated connections, even though the mathematics is very simple. And what do? Well, they connect your temperatures, your humidities, all the different predictors. They all get in a big melange mixed together, and then out the other side come your fluxes or your heating rates for the system. And there's very little prior information about how the physical process goes on. So one of my collaborators, Peter Jukkonen, devised a really nice model to try and mimic the physical process that's already going in, and therefore bake in as much physical prior information into the system as possible. And so this was to say that for shortwave heating, we know a lot about the directionality of the physical process. So we have incoming solar radiation, and it's going to interact level by level and descend through the atmosphere. And so what we're going to use is a recurrent neural network, which is often used to propagate forward in time, but we're going to use it to propagate down through the atmosphere, and then we're going to put some others to allow back up the atmosphere. And these are trying to replace the absorptions and the reflectances and the interactions with gases and aerosols. And what the advantage of this is, it means that the physical system you're solving at the top of the atmosphere is going to be the same as the physical system you're solving at the bottom of the atmosphere, which is a nice prior that we think we should bake into our system. And so what this does, this results in a very small number of trainable parameters than if I tried to replace this with, I have too many slide transitions, don't I? Some giant system like this that has no prior information, and in fact just outperforms flat out, has a lower offline error than my sort of knowledgeless system. And we can do a similar thing for the long wave process. When we're doing this sort of building a machine learning architecture up from the base, we really need to be thinking about what's the directionality of our system, what information we need to do. So for long wave, the directionality is more coming from the surface, but we can have a similar model that imposes this. So what does this then look like? So these are some random profiles of the atmosphere showing you the down fluxes, the up fluxes, and then actually how much heating it has on the atmosphere. These plots should all really be tilted. They're better this way because model level is an input and the output is our heating rate, but actually the atmosphere is vertical, right? So at the left is the top of the atmosphere, on the right is the bottom of the atmosphere. We have about 100 layers in our model, and in each of these columns, in each of these 3 lines, there are 2 lines, but certainly with this resolution on this screen, you can't see the difference. Because we do an extremely good job, we have an error of about 1 watt per square meter within an order of sort of 600 and about 10 to the minus 2 kelvins per day. So we do a really good job by baking in as much physical prior information as possible. However, one of the other things we've learned in this field when we're trying to create emulators or learn new parameterization schemes is there can be a big disconnect between a great model offline and a great model online, which we heard about a bit before. So you shouldn't get excited. You shouldn't even, in my opinion, be able to publish works if you've not done this online coupling. So thankfully, I've not come to you without anything. So this is how we do online. So these plots are relatively complicated because they're the ones we use sort of by standard. So let me explain through. This is me doing a suite of forecasts over a summer period. This is run at about 30 kilometers, so not our operational resolution, but something really quite a high resolution and forecast. And this is different forecast lead times, so 12 hours, 24 hours, 48 hours, going out in time. And this is seeing whether my forecast got more or less accurate when I used a neural network in replacement of our existing radiation solver. And we shouldn't really see blue because all I'm trying to do is recreate the model. So the blue you see here is spurious because it indicates a slight improvement, but it's very small. And the red indicates some degradation. And we haven't done a perfect job. That might almost be worrying at this step if we manage to create those errors down to 0. But what we have done is we've got no errors down at the bottom of the atmosphere, and we've restricted so far our errors to quite high up in the atmosphere. So there's room for improvement, but the model's already performed quite well, particularly given that most of the sort of headline skill we'd be looking to sort of sell people on happens lower in the atmosphere, right? Not many people live up above 100 hectopascal. So what about speed? Because the purpose of doing this was to make it faster. And here I have arrived a bit early because I have some preliminary results, which is that on a CPU technology, we are slightly faster, but the GPU where we're really looking to do stuff, this is ongoing work. Decoupled, it's a much faster, but the proof of it is in the pudding, and connecting GPUs into our integrated forecasting system is quite a computational challenge, quite a complicated challenge. So, that's sort of a maybe in terms of sort of operational forecasting. What about a second one? Can machine learning add extra spatial resolution? So this is all an example to show you pictures of my dog. That's the whole reason I came and gave this talk. But just to teach you, the tool we're going to be using here is conditional generative adversarial networks, or GANs, or CGANs. And how these work is the following. You would give it some conditioning, some input, and you would give it a random noise. And then for each random noise system you send through, you would get a different image of a dog. Here, my sort of fake problem that I'm synthesizing is turning cartoon animals into real ones. And the beauty of this is we can generate an ensemble of possible solutions, which is very useful for underdetermined problems. Problems where I have, for one possible input solution, there's a whole space of possible output solutions. For example, there's not one unique way of converting this dog. So how about for actual weather forecasting rather than pictures of my dog? Well, the equivalent framing of the problem here, conditional GANs for rainfall prediction, is as follows. So we take 10-kilometer model rainfalls from our IFS forecast. We take high-resolution orography to give it as much possible chance to sort of learn the impact of this as possible. We provide some noise, and then what we're looking to map onto is some radar data. This is actually higher resolution than this. This is a very bad quality photo that I've put in. It makes it look like I'm still working at a very coarse resolution. This is, in fact, 1-kilometer radar observations. So what we're asking a model to generate 10 times or 100 times, if we think about the area, as much volume going from 10 to 1 kilometer. So the second trick one has to do here is not use mean squared error, which is the sort of the mainstay of the problem, and that's because that will almost certainly lead you to get very blurry predictions, because mean squared error encourages you to not be bold. It encourages you to be very cautious, and you get what people already predicting rainfall know of as the double penalty term, which is better to make a very low prediction rather than to make the right magnitude prediction but put your cloud in slightly the wrong place. And so the way this trains is we don't actually use a conventional loss, but we use a second whole neural network whose whole purpose is just to detect true from false. So it learns to spot the real dogs from the fake dogs, or the real radar images from the fake images, and this information can be propagated backwards to encourage the generator, the thing that's building these synthetic images, to create as good an image as possible. And so then we get to some results. So what I have here is a single instance over the UK, which is where we focused our study here. So our inputs are things like total precipitation and maybe some other atmospheric predictors that we think are really important, plus our orography. This is the radar image that we're trying to get to, and this is not time, this is ensemble members. So I'm drawing, and as Tim alluded to earlier, I can draw lots and lots and lots for very cheap ensemble members. And what I'd like to do is not just get pretty pictures, but get something that's well calibrated, by which I mean that this radar image is a plausible member of this ensemble, so it could be any member. And the way we would test that is if we would look at where the ensemble member came on, say, rainfall, the normalized occurrence, or the cumulative, the CDF, we would want a flat line here, or we would want a linearly increasing line here. We don't quite get that. It's still a very hard problem, but we get something that's really rather flat. So that means that the model is not just producing pretty pictures, but it's producing quite well calibrated pictures. If we take the ensemble mean, we get back to something that's not identical because there was some bias term in here. We've not just undid this step. But the key thing is not in this ensemble mean. That's not very useful information. What the GAN's able to do is if you look in some of these instantaneous realizations, you'll say there are some lighter colors where we've predicted stronger values of rainfall than the raw model was able to do. And these are plausible with where we got stronger rainfall in our ground truth. So these are just a couple of components that we are imagining, but in fact there's a whole host of problems that we are currently working on and other centers around the world are working on. This is a very exciting time to be at this intersection of machine learning and weather forecasting. So just to take you on a whistle-stop tour of this, so you could think of using transformers, if anyone's familiar with the tool from natural language processing, as an architecture to be useful for ensemble forecast post-processing. That's really useful because natural language processing has to deal with words and sentences as coherent structures and transform them together. We can think of it this way as ensemble members. You want to transform the ensemble together while dealing also on an individual by individual member basis. Graph neural networks are going to be very exciting for working on the sort of unstructured grids that we use in our operational forecasting model. Data assimilation, the way of going from observations to an initial state of the atmosphere, is in itself very much like a machine learning problem, but there are very exciting areas in either learning a bias within the variational framework where you get the initial condition, or in fact taking the models we derive from radiation and using them to generate some of the components we need to do this 4D variational technique. This has gotten a bit into the jargon-heavy world, but if you want to learn more, come and talk to me afterwards. We just held quite an exciting sub-seasonal to seasonal forecasting competition. So this is looking at trying to forecast on the sort of 3, 4, 5, 6 weeks time scale, where we know the model has some skill, but a lot of the time climatology is best. And people were able to beat our operational weather forecasting model not by replacing it, but by augmenting it, adding to it, and learning to mix our operational model with other centers' operational models to blend together the best possible scoring sub-seasonal forecast. We heard about atmospheric chemistry, and I touched on observation operators before. However, This is not a panacea, as Tim, I think, used the word before. As there are opportunities for machine learning in weather forecasting, there are most certainly challenges, particularly going to operational machine learning in weather forecasting. So a few of these, just to sort of give you a picture of this, the changing model cycles. So on a yearly basis, we are changing our model. And this might mean that the temperature bias over the UK has flipped its sign from being slightly too warm to slightly too cold. So a machine learning system has to be ready to adapt to this and be useful almost immediately after we upgrade our model. So perhaps this is a perspective for transfer learning. We heard from Henrik earlier about stability, how vital that is. We can't be putting something into our model if it's not going to give us the sort of a forecast every time we need a forecast. Trustworthiness is a very hot topic at the moment. What do we need to get a model to bring machine learning into our forecasting system? Can this be achieved just by a, say, infallible data split so that you've proven that your model really has generalized outside of your training data set? Or are we going to need interpretability tools, which are very sort of a la mode, to convince people that this is the right approach? The climate, as Tim alluded to in the previous talk, lends to additional problems, but there's some work on trying to normalize our data so that it looks at one level sort of climate invariant. And then the final aspect is just about connecting the whole world of machine learning operationalization, which exists in places like Amazon or Google, and connecting it up to our forecasting systems. They all have different sort of ecosystems. So how do we do this? This is unfinished. This is very much a next challenge for the community. If you look at the archive or if you look in your favorite journal, you will see a phenomenal amount of papers published about how machine learning can help in weather forecasting. But we're now, I think, moving from the sort of explore phase to the exploit phase. We want to be transferring these exciting solutions into an operational setting. So let's see how that goes. Thank you very much.
Any questions?
Yeah, more a little bit of a comment or even answering your question. And in terms of using this in operations, we've been trying pretty actively to get this more actively done within NOAA. And there's basically two things that are a problem with that. One is that there's a lot of very interesting work that's done with machine learning and AI, but it's all prototypes. And then we stop and we say, somebody else should pick it up and make it machine. So we need to make it sexy in this field to not only show that it could be done, but it can be done all the time. And the second one is actually much more of a cultural issue, or if you want to be negative, you can call it political. I don't know, one of the reasons why I don't have much hair anymore is that you go have a competition where you have some money to do research on topics including AI and machine learning, and then you go to a reviewer to look at the scientific value of the proposal. And then the reviewer goes like, yeah, this is machine learning and AI. If I do this in operation, then I have to retrain this every single time I upgrade my model. And what is really frustrating is that same reviewer is the guy who's doing the statistical correction of the model and has to redo it every single time. And so we have to kind of work our way through, in the sense that the people who make the decisions and who decide what goes into operations also start getting into this cultural mindset that it is okay to look at something new, and something new is not necessarily a risk, like a lot of people see. So, sorry about that.
Any more questions? Any more questions?
If there's no more questions, I might just do a quick, well, advertisement is maybe a strong word, but if you found this talk interesting and you'd like to try your hand, one of the things that we put together with the funding that pays for me at the moment is trying to create some interesting benchmark data sets and solutions so that people can come into the field, so we can get machine learners from outside of weather and climate forecasting and get them to work on these things. So we've got these sort of 5 different applications. All the data is published. We're trying to publish all our tools as well so that you can really drop in and try and help make a difference. So yeah, have a look at that.
All right, okay. Thank you very much. So if there are no more questions, let's thank Matthew again.